Hello everyone, welcome back. Today we're going to work on some practice problems for rotational kinetic energy. But a few quick things before we start those. One, this is probably going to be the last video in the rotational portion of this series, so this also will probably be the last time you see our linear to rotational chart, which you should definitely write down somewhere. Today we're going to concentrate on this one, rotational kinetic energy, but as stated in my last video, we're probably not going to be using this equation too much. Instead, we are probably going to be using one of these, because as we derived recently, the rotational kinetic energy formula is the same for everything if you're talking about rotational variables. But when you convert them to linear variables, the equation is different because the moment of inertia of these three different shapes are different. So again, we have the ring, cylinder, and sphere, and we do not have the point mass because the point mass can't roll. For the sake of time, I'm going to work out the algebra and get to a point where you can just do plug and play on your own. If you wish to check your actual final mathematical answer, I will put that in the notes for this video. So without further ado, let's check out our first problem. A solid sphere starting from rest rolls down a 3-meter high hill onto flat ground. What is the velocity of the ball after it reaches the base of the hill? So here's my initial point. The ball rolls down the hill. Here's the final point when it's on flat ground. We're going to assume no change in velocity in this section, so you can also put the final point at the very bottom of the hill if you wish. This represents the height, so we have a height initial and a height final of 0. All right, let's list givens. Height initial is 3 meters, height final is 0 meters. Now, if you note, we have very few givens here. So how are we going to find this? Well, once you recognize it as an energy problem, the first thing we need to do is make an energy bar chart. Again, the work column always goes in there, whether you know you're using it or you are not. We definitely have gravitational because we begin with a height. When the ball is at the base of the hill, it rolls down the hill. We have kinetic final and we have rotational kinetic final because the ball is rolling. So my bar chart looks something like this, although this is probably not split evenly. For now, I'm just identifying that all the gravitational is split into kinetic and rotational kinetic. Okay, I'm going to drop the equation down. mg height initial equals 1/2 vf squared, that's the linear, plus 1/2 I omega final squared. Now again, this is a solid sphere, so I'm going to rewrite this and change this last one to its linear variables. And the linear rotation equation for a sphere was 2/5 mv squared. Now we just need to isolate vf. To start out, notice if we divide by mass, all these masses cancel because they're in every part of this equation. Then I'm going to multiply everything by 10. This will be 10g height initial. 10 divided by 2 is 5, vf squared. 10 times 2 is 20. 20 divided by 5 is 4, vf squared. This is going to be 10 gh initial times 9 vf squared. I'm going to divide by the 9 and square root. I am also going to flip these sides and put vf on the left. This is 10 g height initial divided by 9 square root. So if you notice, we have very few givens, but g is a known constant on Earth, and we do have the height initial, so you have everything you need to get your answer here. And no moment of inertia or angular velocity required. All right, that's problem 1. Let's move on to problem 2. A disk is rolling on flat ground at 5 meters per second. It then starts to roll up a hill without slipping. How high will the disk go? So for starters, here's our picture. The disk starts out down here, so this is our initial point, goes to the right, and then moves up the hill. And the final point will represent the highest it goes. So this is height final, which is what we're looking for. And height initial is 0. Now, before we start this problem, there is something else we need to discuss. And it has everything to do with this very important statement over here. The fact that the problem says it rolls up the hill without slipping. For one, that confirms that it is rolling up the hill. But there is something else that it implies, and to do that, I'm actually going to use a zoomed-in drawing of the situation. So here is my disk. It is spinning clockwise to roll up the hill. If it is rotating clockwise without slipping, that means there is friction between the disk and the hill itself. Except in this case, the friction is not slowing it down as if it was a block. If this was just a block sliding up a hill, friction on the block would be against the block and would be slowing it down. In the case of the rolling disk, it is rotating clockwise and it is exerting a frictional force on the ramp that is downward. So in other words, this rotating object is pushing the ramp downward. And if the cylinder is pushing the ramp downward, there must be a third law pair. In other words, the third law friction pair is on the cylinder up the ramp. So this is force cylinder on ramp right here. This is force ramp on cylinder. I'm just using force friction as a shortcut. Now, this force is doing two things. One, since its direction is literally up the ramp, it is helping the cylinder to literally move up the ramp. Two, if the rotation of the sphere is clockwise, and we take a look at the direction of force from a rotational aspect, the direction of the force on the disk is counterclockwise, which means it is providing a counterclockwise torque. So this disk has a positive angular velocity, but a negative torque. And if there's a negative torque, that means there's a negative angular acceleration. If I put these two things together, that means the angular velocity will decrease. It's just like if I said I have a positive velocity, but a negative net force. A negative net force would mean a negative acceleration. If I have a positive velocity, negative acceleration, that means the object is slowing down. That's exactly what's happening here, except rotationally. And if the disk is slowing down rotationally, it is losing rotational kinetic energy. Well, energy can't be destroyed, so where is it going? If that kinetic energy is being lost, and this force is dragging it up the hill, that means it is going into gravitational potential energy. So in other words, we have two types of energy that are going to gravitational. One, the linear kinetic energy just from it moving, but as the disk slows down rotationally, that rotational kinetic energy is being transferred as well into gravitational potential energy. So the picture I'm drawing would be more something like this. Linear kinetic is becoming gravitational and rotational energy is becoming gravitational because friction is literally dragging this up a hill. If you're having trouble wrapping your brain around this, imagine you're on a bicycle and the bicycle is at rest on the hill. You pedal to turn the wheel. The wheel grips the ground, tries to push the ground this way. The ground does not move, so the ground pushes the bike up the hill. So friction between the bike and the ground is exactly what causes the bike to start moving up the hill. If the hill was a sheet of ice, there would be no friction, and you absolutely would not be going up the hill at all. So in short, friction gives grip and allows the rotating object to be pulled up an incline. Okay, back to our problem. Let's list givens. Initial velocity, 5 meters a second. Vf is 0 meters a second because at the very highest point, it is not moving linearly, and as we just discussed, it is not moving rotationally. For a brief moment, it completely comes to a stop. Height initial 0 meters. Height final is our unknown. Let's make a bar chart. Initial state, kinetic because it is moving linearly, and kinetic rotational because it is rolling. So we have both of these. Final state has a height, which is screaming gravitational potential energy, and as we just discussed, both the linear and kinetic are being fed into the gravitational. I'll jot my equations. 1/2 mvi squared plus kinetic rotational. This is a disk or cylinder. I'm just going to go straight to the linear version. 1/4 mvi squared. mg height final. This is all one object, so again, the masses cancel. I'll multiply everything by 4. 4 over 2 is 2, vi squared, plus 4 over 4 is 1, vi squared. On the right, I have 4g height final. These two will then combine. I'll get 3vi squared. Right stays the same. I'm going to divide by the 4g and then flip this around, putting height final on the left. That will give me 3vi squared over 4g. We have vi, g is a constant, so we have everything we need to get the final height in this situation. Now I'm going to take this problem and I'm going to change one thing. And the goal is going to be to really get across what was going on here with the friction pulling the cylinder up the ramp. All right, so even though it's just an adjustment, I'm going to call this next problem, problem 3. All right, so this time I added one more thing. A disc is rolling on flat ground at 5 meters per second, then starts to roll up a hill that is covered in a frictionless oil. How high will the disc go? So this problem starts at exactly the same. Initial point, it is rolling to the right. It rolls up the hill. Final point, it's at some point up the hill. Height final is unknown. Height initial is 0. Start by listing my givens. Initial velocity is 5 meters a second again. The linear final velocity, again, is going to be 0 meters per second. So here's where things start getting different. This hill is covered in a frictionless oil. And if there's no friction, there is no force on the disk up the hill. And if there's no force on the disk up the hill, there is no torque to counteract the clockwise angular velocity. In other words, if I go back to this picture, these forces do not exist. It's a frictionless oil, so there's no friction. If there's no friction, there's no torque. If there's no torque, there's nothing to slow down the angular velocity, which means this disk is still spinning. If I now make an energy bar graph, initial state, I have kinetic plus kinetic rotational. So I have sum of each. Final state, I have gravitational potential energy, but I still have the rotational kinetic energy. There is no friction to slow down the spin. And if I take a look at what I have right now, here is the initial kinetic rotational, here is the final kinetic rotational. If I subtract this value from both sides, they will both cancel. Since there's only one disk, there's only one moment of inertia, and since there's no friction on the hill, the angular velocity does not change. Therefore, kinetic rotational is the same for both initial and final. Therefore, my formula becomes kinetic, which is 1/2 VI squared, equals gravitational, which is mg height final. I'm just going to divide the g and flip the sides. So height final is on the left, we VI squared over 2g. Now, this is with the oil. I'm going to take this and I'm going to put it next to the last problem where there was friction. Notice I have VI squared over g and VI squared over g. But notice this one is 3/4 VI squared over g, or 0.75. This one is 1/2 VI squared over g, or 0.5. This one is bigger because it has the kinetic rotational energy going into the gravitational, as well as the linear. So that disk is dragged up the hill and ends up higher than if the hill had a frictionless surface. So in problem 3 here, no rotational energy converted at all. Therefore it canceled, and this was just a straight kinetic to gravitational problem. All right, these problems are all well and good and nice and neat if there's only one object because mass cancels. But let's bring up a problem where there are two objects. A string is wound around a 0.25 kilogram cylindrical pulley. It is then attached to a hanging 0.13 kilogram mass. If the system starts from rest, what is the velocity of the mass after it has fallen a distance of 4 meters? So in this case, we have two objects. We have the pulley and we have the mass. There is a string attached from the mass that is wrapped around the pulley a number of times. And it is important to note that the string is wrapped around the outer radius of the pulley, because that means the velocity of any point on the edge of the pulley will be the exact same velocity of the string moving down and the exact same velocity of mass B moving down. So I will label the pulley A and I will label this mass B. Let's list givens and see what we have. Mass A is 0.25 kilograms. Mass B is 0.13 kilograms. The block starts here and moves downward a certain height. So I'll call this height initial and height final. Height initial is 4 meters. Height final is 0 meters. Let's make a bar graph and see what's going on. Okay, initial state, nothing is moving, so there's no kinetic because the system starts from rest. However, mass B has a height. So we have a gravitational potential energy from mass B. The pulley is not going anywhere. It's not raising up or down or anything. So it is not changing height, so I'm not going to worry about its gravitational potential energy at all. So mass B has gravitational potential energy. Final state. Mass B will be all the way at the ground, so there's no height, so there will no longer be any gravitational. However, it will be moving because it will be hitting the ground. So I'm going to add kinetic energy for mass B. And as mass B is falling, it will be gaining linear velocity, and the pulley will start spinning, so it gains an angular velocity. And if it gains an angular velocity, that means it gains rotational kinetic energy. So I'll list kinetic rotational for A. and the potential energy that object B had is split into the two of these objects. Object B now has linear kinetic, and object A now has angular kinetic. Time to drop my equation. Gravitational potential energy is mass, but I have to account for the fact that this is mass B. Mass B, G, height initial, equals kinetic for B, 1/2 mb vf squared plus. So again, we have a cylindrical object, so I am going to use a linear version, which is 1/4 mv squared, but this has to be mass A. I can, however, use final velocity squared here because, again, this radius is on the outside edge of the pulley. So the velocity of this string going down, considering it's all the way in the outer edge of the pulley at the max radius, means the velocity on a point in the edge of the radius and mass B itself will have the same velocity. What I cannot do, however, is divide out the masses because they are not the same, which means the algebra is going to be a little less pretty than last time. I'll start by multiplying by 4. I get 4 mb g height initial equals 4 over 2 is 2, 2 mb vf squared plus 4 over 4 is 1, mass A vf squared. I'm then going to factor out the vf squared. I can see 2 mb plus ma vf squared. I'm going to divide this, take the square root, and then flip sides. That gives me vf equals 4 mb g height initial over 2 mb plus ma and square root to get rid of the squared. As a quick check, we have mass B, G is a constant, we have no height initial, we have mass B, and we have mass A. So once you plug and play numbers and units, you will get the final velocity of mass B as it touches the ground. Now, once you understand that there are two different masses in this problem, it's not that bad. And the fact that the string wrapped around the outer edge of the pulley made this kind of straightforward, even though it obviously looks a little messier than our previous problems. However, while we're here, let's go up a level, and for our last problem, again, I'm going to make one change. And that change is going to be, what if we have two different objects and two different radii? Let's check it out. All right, so here's the same problem with one important difference. A string is wound around a 0.25 kilogram cylindrical pulley, but at 1/3 its radius. It is then attached to a hanging 0.13 kilogram mass. The system starts on rest. What is the velocity of the mass after it is falling a distance of 4 meters? So to start out, we have the same mass A and mass B. Same height initial, same height final. Most of our givens have not changed, so I'm just going to put them here. All right, here's where we get to the important part of this problem. They say the inner pulley has a radius of 1/3, but to make things a little easier for the math, I'm going to make that inner radius R, and therefore the outer radius to the disk is 3R, because I find the multiplication to be a little easier to deal with in the math than fractions. Now, one thing we can notice right away is that if this string is pulling down on the pulley and the radius is 1/3 the radius, that means the torque produced is going to be smaller because, again, torque is force perpendicular times radius. And if that's true, then due to rotational second law, then the angular acceleration will be smaller. So we're not adding a second pulley here. There's all the same pulley. There's just something massless here that the string can wrap around. So if torque is decreased, angular acceleration is decreased, and if angular acceleration is decreased, then linear acceleration is decreased. So basically put, the entire pulley is going to speed up. And if that is true, we are expecting a smaller answer for our final velocity here. Now, the most important part is going to come down to this equation. The velocity of B is going to be omega times RB. Radius B is going to be the radius here, the smaller radius, where the string is wrapped around the inner part of the pulley. A point on this inner ring is giving the same velocity of the string that is moving in a linear direction. And since the string is attached to mass B, velocity B is omega times the radius of B. Now, the inner pulley and outer pulley have the same angular velocity because they're literally attached to each other. And if that is true, we come to a very simple but important conclusion. If the outer pulley itself is 3 times the radius of the inner pulley, then a point on the outer radius is going to have 3 times the velocity. So I'm comparing a point here, which I'm calling B, and I'm comparing a point here, which I'm calling A. If this pulley moves around a circle, A is moving 3 times faster than B. And if we go back to our original derivation for angular kinetic energy in linear terms, the radius we had to use was the actual radius of the disk or cylinder. So basically put, if the radius is 3 times larger, the velocity will be 3 times larger as well. Let's make our energy bar chart. Again, object B is gravitational. Nothing is moving at the start, so there's no kinetic at all. So it all starts with gravitational potential energy for B. Again, object B is going to have linear kinetic, and object A is going to have rotational kinetic. And the energy is going to split between both of them. I'm not trying to make this a perfect ratio, but at this point, I definitely know that the pulley is going to have more kinetic energy than mass B because of that larger radius. So gravitational potential energy, mass B, G, height initial, equals 1/2 mass B, VF squared, linear kinetic, plus. Okay, now here's where things get interesting. Here's a disk. I'm going to use the linear version of rotational kinetic energy, 1/4 mass A, because it's the disk, and this velocity is going to be 3 VF squared from here. And to be clear, this final velocity is for mass B, because that's what we're looking for. And again, whatever velocity mass B has, a point at the edge of this pulley is going to have 3 times that velocity. That means my equation is actually 3 squared, which is 9 over the 4, mass A, VF squared. So this is kind of what I meant by most of the energies going into the pulley. I'm going to multiply everything by 4. It gives me 4 MB GH initial. 4 over 2 is 2 MB VF squared. Here the 4's cancel to make it 9 mass A VF squared. Again, I'm going to factor out the VF squared. Let's make some space to make this smaller. Last step, I'm going to divide this out, then take the square root. I'm also going to flip it so VF is on the left. That gives me VF equals 4 MB GHI over 2 MB plus 9 mass A square root. So this is our final velocity for mass B now. And if you remember, we made a prediction that this would be lower than the previous problem. Well, this is the velocity we got from the previous problem where the string was wrapped down the outer edge of the pulley. Notice the only difference is this 9 here. And if this is in the denominator, that means our final answer is going to be smaller than our answer from the last problem. So that passes a red flag right there. So if you notice, they're not too much different, but the real key to this was this step right here. Recognizing that if the outer radius of the pulley is 3 times larger than that inner ring, a point at the outer radius is going to have 3 times the velocity. The gravitational potential energy is split between the two, but if you lower the inner radius or increase the outer radius, that energy split will give more to the rotational kinetic energy of the pulley and give less linear kinetic energy to mass B. All right, if you have gone through this entire video with me, you are very well prepared for rotational kinetic energy because we literally just did about 90% of problems I've seen on AP exams. As promised, I'll put the final answers in the notes for this video. And since I believe this video will be the last in my rotational physics series, I'm going to end it with this screen, which is all our linear to rotational equations. Other than that, have a good day. This is Mr. M, signing off.